Thank you and good evening, Knutsford. This is the ABC of galaxy evolution. Yes, I hope to convince you it is as simple as ABC, but perhaps the ABC isn't quite as simple as we would like it to be. We all know what galaxies are, I assume. We look out into the universe and we see there are quite a few of these out there. Okay, 100 years ago, we weren't sure what these blurry things in the sky were, but thanks to Hubble and a few others, we've now convinced ourselves that these objects are not within our Milky Way. These are galaxies in their own right, and there are lots of them out there. It's difficult to count them all, but from looking at a small patch of sky and extrapolating, there's probably 1 trillion of them within the observable universe. Of course, we can't tell what's beyond the observable universe by its very nature, but it looks like there's at least 1 trillion or 2 that we can actually observe. A lot of them look similar, a lot of them look different. Some of them are beautiful spiral structures, some of them are isolated, some of them appear to be interacting with their neighbors, in other words, pulling tidal forces, gravitational pulling between individual galaxies. So what I'm covering this evening is basically how do we think they came to be in the first place? How did we end up living in a universe which seems to be full of many billions, if not trillions, of galaxies? So yeah, spoiler alert, I'm going to tell you up front what I mean by the ABC. I have given other talks in which the ABC don't get revealed until later, but in the case of galaxies, I thought it's just as well to be upfront with what we're talking about. So the A of the ABC refers to accretion. This is how galaxies form in the first place. Matter created in the Big Bang, the subject of a completely different talk. Matter created in the Big Bang made all the hydrogen, and that accreted to form the galaxies in the early universe. Exactly how early did galaxies start to form? Well, that's the job of the James Webb Space Telescope, to look back in time to try and work out exactly when this actually happened. We think there are black holes at the centers of every galaxy. Possibly not every one, but certainly they seem to be very common. It looks like there is a black hole at the center of just about every galaxy that we have a look at. Some of them are very active, meaning they are feeding, matter is falling into the black holes, and in some cases there's very little matter around the black hole, so matter is not falling in, and those would be regarded as quiet or quiescent black holes, like for instance the one in the center of our galaxy, not particularly active. And the C of the ABC stands for collisions. This is not as apocalyptic as it sounds. Galaxies collide all the time. It is part of the natural phase of evolution of galaxies to collide with other galaxies. It's not a rare event. Okay, it doesn't necessarily happen that often for any given galaxy, but when we look out into the universe, we find it's going on all the time, and we think it's likely to have happened many times in the history of any given galaxy, including our own Milky Way. So galaxies grow by colliding and merging with other galaxies. In other words, galaxies are cannibals. That's how they live, that's how they grow. So where does the story of galaxies start? Well, like any good story, it starts at the beginning. And in this case, that means the beginning of everything. A talk I gave you, I don't know, about 5 years ago, perhaps, something like that. So the beginning of everything describes how the universe came into existence. And it is believed that if we live in a universe in which everything appears to be expanding, all the distant galaxies are moving away from each other, if we wind the clock backwards, that would imply that everything that is currently in the observable universe spread over a volume of some 100 billion light years in diameter, everything used to be an awful lot closer. All of those objects, all of the matter dispersed over hundreds of billions of light years used to be separated by centimeters. if you go back far enough. What I like to think of as the cosmic golf ball. Not only does that give you an idea of how small the observable universe was in the very early days, very early fraction of a second of the universe, but also we think that there were fluctuations, quantum fluctuations. We're not going to go into quantum theory this evening, but we believe there were dimples in the golf ball, small variations of temperature and pressure, which ultimately gave rise to the large-scale structures in the universe. We see those structures imprinted in the cosmic microwave background. The universe might have started very small, and it might have grown from the size of a golf ball after many hundreds of thousands of years. Eventually it turned transparent. That's when atoms started to form and the universe became transparent. The universe would have been huge at that time, started off the size of a golf ball, but it would have been millions of light years across by the time it turned transparent and released the light that was in the universe. And that's the light that we see stretched out from originally being visible light, stretched out now into microwaves. And that's what we see across the entire sky, a microwave background, which is the result, the little stipulations, the little mottling that we can see in the microwave background. It's relatively smooth, but when we look at the individual intensities at each part of the sky, we find small variations, and that's precisely because the original golf ball had small dimples in it, small fluctuations, which eventually became the ripples in the microwave background. And when you allow gravity to take hold of those small variations, ultimately that gives rise to all of the large-scale structures we see in the universe. So we can ask the question, how do we know exactly what happened in between knowing that light was released that is now visible as the cosmic microwave background? How do we get from a universe which is effectively a lot of microwaves, as we see it today, to all of the structure? Here we see a Hubble Deep Field, lots of galaxies existing across the universe. Well, apart from saying we think we understand the physics, well, that's the starting point, not the ending point. A lot of what we think we understand about how galaxies came to be is based on simulations. We need the basic physics to understand, but simulations have allowed us to say, let's program the physics into a simulation and run a simulation and let gravity do its stuff and see how we can go from something which is very small and dense and hot to something which is much larger and cooler and expanding. Can we see where all these structures come from? I'm not going to go through all of the simulations that exist. People over the last 10 or 20 years, thanks to the advances in computing technology, have been able to run effectively simulations of the universe. And these simulations look for different features of the universe or perhaps operate on different scales. I'm just going to pick one suite of simulations called the illustrious simulations. They seem to do the job of illustrating what I want to show this evening. So I'm not saying there's anything limited by the other simulations. Illustrious just happens to be the ones I've chosen in this particular presentation. So very early universe. The universe started very small with dimples in the golf ball, which ultimately gave rise to variations in the microwave background. But can we understand with any sort of simulation how we go from a universe like that to a universe full of galaxies? Well, I'm going to show you the result of one simulation in which we're taking not the entire universe, we're taking a large cube, filling it with matter, putting in small variations. The amount of blue, the lightness of the blue, is an indication of the density of material. It might look relatively uniform, but there are actually small variations in the density of matter in this particular simulation. We're then going to run the simulation and let gravity do its stuff and see what happens and ask ourselves, what do we end up with after billions of years? Does it look anything like the universe we see today? Let's run the simulation. Brighter means denser. and hotter in this simulation. And you can see that already we're starting to see structure in the large-scale structure of the universe. It's starting to form a web-like structure. And where these web filaments meet, you get very high densities and high temperatures. This is where galaxies are starting to form. Not necessarily individual galaxies. It could be clusters of galaxies or superclusters of galaxies. But simply by allowing gravity to do its stuff over billions of years, we can start with tiny variations of density, and then gravity effectively amplifies those. Bits that are more dense start to collapse, and that produces more gravity, which then pulls in more matter, which gives you higher density, etc. So some parts appear to be relatively empty, the darker areas here. Some parts are very bright. That's where we get the galaxies forming. And there are this web-like structure of filaments as well as voids. And where these filaments tend to meet in a knot, that's where we get matter forming. So most of the simulations agree that if we run simulations of the early universe, it looks like we end up with a web-like structure. And as best we can tell, when we look during the simulation and ask what is actually happening to all the matter that's there, the matter seems to flow down these filaments and collect in the areas that we identify as where these filaments meet. That's where the galaxies are forming. Matter flows through the filaments. So the filaments form because matter is flowing and starting to condense into these high-density regions, which ultimately we identify as galaxies. Various simulations have started with different initial conditions, and they all seem to give the same sort of indication of that's why we have a web-like structure in the universe. And that is indeed what we see. When we look out into the universe and look at all the galaxies that are out there, the galaxies are not uniformly distributed throughout the entire universe. They seem to collect together in clusters, and those clusters seem to line up in these filaments. And these filaments do seem to go across the universe and separate areas where there's very little in the way of galaxy formation, these voids that we can see here. So these simulations do seem to give us the universe in which we live, which is why we have some confidence that this is indeed a realistic simulation. But it's nowhere as simple as I have implied at this point. It's not simply a question of start with lots of matter, let gravity do its stuff, and just sit back and wait. You do have to put in a certain amount of physics, especially you have to take into account the fact that stars will be born, and stars will live, and stars will die. And when stars die, you can get supernova and you can get black holes forming, and this will ultimately give rise to outflowing matter. Gas can be blasted out by black holes, by supernova. So although gravity is trying to pull everything together to make galaxies, when you start to make stars, effectively the stars push back. And stuff made from stars, especially when stars come to the end of their lives, will start to push back and start to impede any matter that's falling in, trying to flow down the filaments to make the galaxies. So we can ask ourselves, even if we get a universe which is full of these filaments and this web-like structure, even though the simulations say that's what we can expect, can we explain all the diversity of galaxies that we see out there? Some galaxies with very clear spiral arms, some with less distinct spiral arms, some with 2 arms, some with 4 arms, some with perhaps almost no visible arms at all. Some galaxies are quite definitely spiral in structure. They are disk-like galaxies, which, when seen from above, have spiral arms. There are other galaxies, seen here on the right-hand side, which don't appear to have spiral arms. They appear to be a little bit redder in color. They seem to be football-shaped or rugby ball-shaped, elliptical, but not the same disk-like structure as spiral galaxies. This is a collection of known galaxies which have been thrown into this grid just to remind you of the diversity of galaxies that exist. Question: do our simulations actually produce this sort of diversity of galaxies? So let's have a look at the first set of simulations and see how well it does in terms of producing galaxies. Let's look at the accretion process. Firstly, just a word or two about the simulation themselves. Remember, I've just chosen one particular family of simulations, the so-called illustrious family. And this is a simulation that runs, roughly speaking, from very early, not far after the Big Bang, all the way to the present day. And then we stop it, usually at the present day, to say, is that the galaxy, is that the universe that seems to be the one in which we live? In principle, we can run the simulations into the future, but we don't know exactly what the future holds, so we can't check it against reality. So a reminder that yes, it's all about matter accretion, A for accretion, and that is under the influence of gravity. But not only do we have to take into account the fact that stars will push back because of black holes and because of supernova, the elephant in the room is, well, actually, the universe is full of a whole load of dark matter, which we don't really understand. But we know it's there. How can we possibly put this into a simulation when we don't know what it is? Well, as far as the simulation is concerned, all we really need to know is how many kilograms of stuff there is out there. And we do know how many kilograms, how many tons, how many stars worth of dark matter is out there. We've got a pretty good indication it's there, even though we don't know what is making up that dark matter. But we do know how many kilograms we've got. We've got this many kilograms of hydrogen, and we appear to have even more kilograms of dark matter. So it can be put into the simulation. And it turns out we have to put it into the simulation. If we try and run a simulation that's only got hydrogen in there, only ordinary matter, we can't get the universe to look the way it does at the moment. If we only put dark matter in there, we don't get stars. We have to put in a mix of ordinary matter, hydrogen, and some dark matter. Only when we put in a mix do we actually get the universe to look right. And that's how we determine, one of the ways we determine whether the universe is indeed coming out the way we think it ought to from these simulations. The illustrious simulations, the first generation of the illustrious simulations, ran in the early teenies from about 2013 to 2015. It involved 20 million CPU hours. So a CPU is simply a central processing unit, think small computer. And so with 20 million of them, 20 million hours worth of those computers running, they produced a simulation of the universe. They then realized the things weren't coming out quite right. They realized they could refine the simulation. So they learned from this first run of the simulations over a couple of years or so, they learned what was missing and decided we need to do a better job of putting in the physics of the supernova, the black holes, of the way stars form, etc. So they produced a more sophisticated simulation. Did they call that illustrious version 2? No. Tells you something about the programmers that were involved, because they decided to call it illustrious TNG. Illustrious, the next generation. You get the reference, yep. And if anybody wants to actually go and look at these simulations for themselves that I'm borrowing, then tngproject.org is where all of these videos can be seen and found and explained. So illustrious TNG, hereafter basically just called TNG for brevity. TNG ran for not 20 million CPU hours, but 200 million CPU hours. It took a few years to run the simulations. On a supercomputer, just to give you an idea, if you wanted to run the same code on a desktop PC, well, you can run it on a desktop PC, but the program would take approximately 20,000 years to run. Something akin to the Hitchhiker's Guide to the Galaxy there. TNG ran on different scales. We want to know about the large-scale structure of the universe, but also we'd like to understand galaxy formation and galaxy evolution. So they actually ran on different scales. They had 3 sets of simulations running, basically 50, 100, and 300, indicating the size of the bit of the universe they were looking at. 50 megaparsecs, 100 megaparsecs, or 300 megaparsecs. And for those who prefer light years, there's the equivalent numbers in light years. They ran on large scales, 300 megaparsec, to try and understand the large-scale structure of this filamentary web that appears to be threading through the entire cosmos. They also ran on much smaller scales so that they could see the detail that we want to see in individual galaxies. And they also ran an intermediate size, TNG 100, just to make sure everything was looking sensible. The large scale and the small scale and the intermediate scale was a sort of a sanity check to make sure that everything agreed with the larger scale and the more detailed scale. So they ran everything at multiple scales to make sure that it was all self-consistent. Just a reminder, astronomers tend to prefer to use light years because that's sort of intuitive. How far does light go in a year? So astronomers, amateur astronomers in particular, prefer to use light years, but astrophysicists will generally always use parsecs. The definition of a parsec is 1 parallax second. At what distance does a star produce a parallax of 1 arc second as the Earth goes round the sun? So a reminder of the sort of scales we're talking about. The Milky Way, just to give you a ballpark yardstick, as it were, Milky Way about 150,000 light years in diameter, so about 50 kiloparsecs. And if we think of the distance between galaxies, let's take Milky Way to Andromeda as a sort of a yardstick. The distance between the Milky Way and the Andromeda galaxy is about 2.5 million light years, or about a megaparsec. So very rough rule of thumb, parsec is roughly the distance between stars, and megaparsec is roughly the distance between galaxies. Not strictly true, but it's good enough to give us a ballpark figure of how the universe works. So let's have a look at one of the TNG simulations. Here we're looking at where a number of filaments meet. Remember, there's a web structure throughout the universe. We think that matter funnels down the filaments and effectively collects at where filaments join. So this is looking at the detail of where 3 filaments meet. There's a filament coming in from the top, one coming in from the left, and I think one coming in from the bottom. And so let's run this simulation over a few billion years and see what happens. Bright means lots of material is collecting, the density is going up. Dark means the density is going down. So material is funneling into this central region, causing this sort of whirlpool, if you like. Sometimes matter comes in and doesn't stay and goes out the other side. But as time goes by, more and more of it is collected by the gravity of the mass that's collecting in the center of these filaments. You can see that it's getting darker and darker in the corners because less and less matter now survives in these areas as more and more of it is starting to collect in that central region. And after a few billion years, you can perhaps start to see, especially if you squint, this is definitely reminiscent of something like a spiral galaxy in which we're starting to see the structures forming. We can't necessarily tell what's going on directly in the center, but we can get the impression as matter falls in from these filaments, as it flows in through the filaments, it starts to collect. It's very unlikely the material all converges to one point and hence will circulate, much like when you take the plug out of the bath. The water doesn't go straight down the plug hole, it tends to circulate before going down. Was there a question there?
Why does it spin?
Because it's very unlikely the material all goes to a point. It is much more likely it misses the central point. So in other words, there's always going to be a finite angular momentum. The same reason the solar system has a finite angular momentum. As material comes in, it is extremely unlikely it all falls towards one microscopic point. It is almost certainly going to miss and therefore produce a rotation. We don't know what the total spin of the universe is, but this appears to be spinning anti-clockwise. It would spin clockwise if you look at it from the other direction, of course. So there's no directionality. This is just, you can choose to look at this simulation from any direction you like. There is no such thing as forward and backward. Therefore, clockwise and anti-clockwise in that sense have no meaning. finite angular momentum will give rise to rotation, just like for the solar system. And yes, there's no preferred direction, and all of the galaxies that we've looked at so far, there appears to be a 50-50-ish mix of those that appear to be rotating clockwise and anti-clockwise as seen by us, but of course that's just as seen by us. From a different viewpoint, the galaxies would appear to have a different rotation. On the largest of scales, here TNG 300, a large-scale simulation has been inverted so you can see the darker galaxy clusters and filaments a little more clearly. And here we've zoomed in to particular regions, tiny little, barely more than specks in the original simulation have been blown up just to give an idea of, we seem to get variations in the sort of structures of galaxies that get formed in these simulations. And the question is, well, do these simulated galaxies bear any resemblance to actual galaxies? And if we compare them, this is a bit artificial because we can simply go out into the universe and look at all the galaxies that are out there and say, do any galaxies look like this pair at the top? Well, actually, yes. The antenna galaxies, if we go and have a look at those, do seem to look a little bit like this pair that have been seen in the simulation. And do we get interacting pairs where one appears to be distorting the other? Yes, we see lots of examples where galaxy pairs seem to be distorting each other. Do we get galaxies that look relatively symmetrical but seem to have shells of stars rather than spiral arms of stars? Yes, we do see galaxies. Real galaxies on the left, simulated galaxies in the panels. Most of the time, the simulations produce galaxies which are entirely plausible in the sense that they are telling us that, yes, it is entirely reasonable that these galaxies result from gravity pulling in and stars pushing out as these galaxies evolve in the early universe. If we want higher resolution, we can't always see the detail of what's going on if we're looking at TNG 300, remember the larger scale, but if we look at TNG 50, looking at the smaller scale with more detail, then we can start to see all sorts of detail in the structures of galaxies. Here, there's simply a panel of 25 examples. You run the simulation, you find what galaxies you produce, and then if you wish, you can pick out the disk-type galaxies rather than the rugby ball elliptical galaxies. And if you pick out the disk-type galaxies, here they are simply paraded in a 5x5 grid, where the color coding indicates where does all the hydrogen seem to go. And you can say, right, if all the hydrogen seems to end up according to the color code on the left, the face on is the top part of each panel. The little line underneath is what does that galaxy look like from the edge on. In other words, these are disk-type galaxies. We've picked out the disk-type galaxies, the ones that appear circular face on, and the ones that appear like a line if you look at them edge on. The left-hand side is basically saying where does the hydrogen end up? And the right-hand side of this, the same set of galaxies, in this case we're saying, well, if we do know, according to the simulation, where the hydrogen goes, let's assume the hydrogen makes stars. That's a reasonable assumption. We know that stars take hydrogen and basically fuse them to make the heavier elements, helium, carbon, nitrogen, oxygen, etc. So let's just assume that if that's where all the hydrogen ends up, let's assume that the amount of hydrogen will determine the number of stars that are made. So on the right-hand side, how bright would we expect the various features in those galaxies to be? Simply based on where is the hydrogen. And therefore, you end up with these images of that's what you would expect the galaxy to look like based on what we understand about stellar evolution. And for those of you who've ever looked through telescopes at the night sky or looked through magazines of galaxies, you will perhaps recognize that, yep, there's nothing in here which looks out of the ordinary. There are plenty of galaxies out there which look like these various disk-type galaxies, these spiral galaxies. Virtually all of them, if you wish, could be matched up to any given galaxy in the night sky. You can almost certainly find a galaxy that looks like this, and a galaxy that looks like that, and a galaxy that looks like this. So again, all of the galaxy structures made by these simulations appear to be a good match to what we actually find in the universe. And perhaps the most important result is the fact you can ask the simulation, well, of all the galaxies you seem to have made by allowing gravity to pull everything together, allowing stars to push back, do you find you get many galaxies like the Milky Way? Our Milky Way has got some few 100 billion stars. We're not sure the exact number. Certainly more than 100 billion, probably less than 400 billion. So somewhere around 200, 250 billion stars. And yes, these simulations do produce disk-type galaxies, spiral galaxies that are about the size of the Milky Way and seem to have the same number of stars as the Milky Way. Face on, they look like a spiral. Edge on, they look like two fried eggs back to back, giving you this characteristic bulge in the middle and a thin line where we have the spiral arms. So yes, these simulations do generate galaxies that look like the Milky Way. If they generated loads of galaxies, but none of them looked like the Milky Way, then we would have a problem, simply because we know that we live in a galaxy like the Milky Way, and Andromeda looks similar, and a few others. We haven't necessarily catalogued every galaxy in the universe, but if it didn't generate a few Milky Way-looking galaxies, we know that it wouldn't be correct. They're there, therefore we have some faith that the simulations are reliable. The B of the ABC stands for black holes because, as best we can tell, the heart of most galaxies, possibly the heart of every galaxy, seems to lie something very massive and essentially invisible. We can see stars moving. For instance, in our own Milky Way, we see stars orbiting around something that cannot be seen. Something is massive enough to make stars orbit very quickly in only a few years. Remember, our sun takes hundreds of millions of years to orbit the Milky Way, but there are some stars that only take a few years to orbit the center of our galaxy. Something appears to be there. The stars are orbiting around something that we cannot see, but must be very massive. So presumably it's a black hole. Simply from how big can it be in order that the stars miss it, it can't simply be a large star cluster. It can't simply be large number of stars in close proximity, because these stars would basically collide with it. It must be something very compact. And when we follow over years, we follow the orbits of lots of stars. Here they are plotted out on the sky, right ascension and declination, so points relative to the center of the galaxy. For years, these stars have been mapped out to see how they are moving by simply using Kepler's laws and saying, well, if we know how far away they are from the central object that's pulling them in, we know roughly how far away the center of the galaxy is. So simply by measuring, we can work out not only the timing of how they're going round, but how far away they are from the central object. We can use good old Newtonian gravity to work out how large the central object is, and it must have a mass of some 4 million solar masses. In this talk and throughout, I'm using M circle dot as a symbol for meaning the mass of our sun. There's nothing special about the mass of our sun. It's just a convenient unit, far better than kilograms or tons, the mass of our sun. So it must have 4 million solar masses in order to make the stars move that way, and it must be really tiny. There's our solar system to scale. So whatever is going on in that tiny dot in the center, it must be smaller than our solar system. It can't be many thousands or millions of individual stars. You could say, couldn't 4 million solar masses be 4 million stars? Well, that cluster would be far too big. We're looking for an object which is no bigger than, for instance, the orbit of Pluto. It's only solar system sized at most, and it's got a mass of 4 million solar masses. And the only thing that fits the bill is a black hole. So this is a picture of the Milky Way seen from the inside, but let's imagine we've stepped out of the Milky Way and are looking back at it. Our Milky Way would look like that, a central bulge, spiral arms outside each way, and right in the middle there, not visible to us because it's just far too busy, much too dusty to see the black hole in the center, but the supermassive black hole, hereafter SMBH, has got 4 million solar masses. That is by no means large compared to other galaxies. For instance, Centaurus, A galaxy, We have good evidence from looking at the way stars are moving in that galaxy that it has a supermassive black hole of 100 million solar masses. And that's not the record. The Sombrero galaxy has got a supermassive black hole of perhaps 1 billion solar masses. They are huge. They're called supermassive for good reason. What happens when a star gets too close to a black hole? It was mentioned earlier, equivalent to spaghettification. A star can be ripped to pieces and will end up funneling into the black hole. Remember, all of the matter can't go straight down into the black hole. It ends up circulating for the same reason we discussed earlier. The material is unlikely to go straight to the middle because effectively that would be statistically very unlikely. It's more likely to miss and end up in a so-called accretion disk circulating around the black hole, much like water forms a vortex before going down the plug hole of a bath. Matter is converted to radiation in the process. Not only is matter effectively stripped off the star, a lot of the matter is converted to radiation. It's an extremely efficient process. Taking a star and using a star with nuclear fusion is very inefficient in the sense that at the end of the sun's life, after 10 billion years or so, 99% of the star is still there. When our sun comes to the end of its life, 99% of the mass it started with is effectively still there. Less than 1% has been converted to energy. Whereas here, it's not a 1% conversion from matter to energy. It could be 10% or 20% or even more. Letting matter fall into a black hole is a very efficient way of converting matter to energy. Some of the energy comes out in the form of these jets, which we don't really understand everything of what's going on there. Almost certainly, it's related to the fact that magnetic fields are getting wound up and are extremely tight in the neighborhood of a black hole. And somehow, the energy of infalling matter gets converted to matter coming out along the polar directions. This is, if you like, the equator of the spinning black hole. The matter comes out along the jets along the poles of the spinning black hole. But it is still an active area of research to try and understand exactly how that works. We know jets exist. For instance, we see a jet here in M87. M87 is a galaxy in the Virgo group, not that far away. It's a long way compared to the distance to Andromeda, our immediate neighbor, but it's close enough that we can see the jet. If we take a Hubble Space Telescope image, we see the jet even more clearly. It is very probable that every black hole will produce jets, and the jets will come out in opposite directions. However, the jet that happens to be pointing in our direction is going to be a lot brighter than the jet that is pointing away from us. So one of these jets happens to be pointing in our direction, and there should be another one on the other side, but it is so much fainter, we basically can't see it. That's the thought about this particular galaxy. In order to see what's going on, given that we need fantastic resolution to see something so small in a distant galaxy, it was decided to link together lots of radio telescopes across the world to make effectively a radio telescope the size of the Earth itself, the so-called Event Horizon Telescope. And this is what they saw, not the black hole itself, but the accretion disk, the material that appears to be spiraling around the black hole. And this black hole, it's been calculated, seems to have a mass of about 6.5 billion solar masses. M87 star simply means the black hole at the center of galaxy M87. It's clearly not completely symmetrical. Again, that's probably because the accretion disk isn't face-on, despite the fact that it looks like a polo mint as it stands. Almost certainly it's actually at an angle, and some parts of the accretion disk are coming towards us and some parts are moving away from us, which means some parts of the accretion disk look brighter than others. And this simulation of what it might be that we're looking at, if we would look at it on the top, we see just a pancake, but if we look at it from the side, it doesn't necessarily look like Saturn's rings, which is what you might expect from a flat object, because the extreme gravity of the black hole distorts space around it. not only do we see the ring on the left and the ring on the right, and we see the back of the ring, we also see the underside of the ring because it's getting the light from this distant part of the accretion disk itself is getting distorted by the black hole, and part of it is coming over the top and part of it is coming under the bottom. So although we're looking at the same thing effectively, light is taking two different paths and being distorted by the black hole. Notice that in this case, because of the rotation, it's brighter on one side than it is on the other in this simulation, and that's why we think the black hole looks the way it does. We see a similar result when we look at the black hole in the center of our galaxy. Our galaxy is much closer, in terms of the center of our galaxy is much closer than the center of M81, but the black hole is some 1,000 times smaller. So the black hole in the center of our galaxy is 1,000 times smaller, but 1,000 times closer than this very distant galaxy with its supermassive black hole. And so the size on the sky was expected to be very similar, and it turns out it was. The size of the black hole that we see in terms of how much sky does it cover is very similar, despite the fact that it's a much smaller black hole. So this is in the center of our galaxy, Sagittarius A star. Seems to have a different pattern of material circulating around. It was a much more tricky thing to image simply because it's a much smaller black hole and everything is circulating much faster. You can't simply assume that if you want to take an image of that, you can simply image for as many hours or days as you want to, because material will be circulating. It's a bit like taking a long exposure of the night sky and having the stars trail. So they had to take effectively lots of short exposures to try and actually identify where these hotspots are and how they might be moving around the central black hole. They've also taken data which indicates the polarization, which way is the light coming. Okay, it's radio waves, but we can still treat it as electromagnetic waves. Which way are they polarized to give us an indication of what the magnetic fields are within the accretion disk. And the magnetic fields appear to do what the theorists might expect if we've got a lot of material spiraling into the black hole. That might go some way to starting to explain why some black holes have jets, but we're not quite there yet. A reminder that the scales are rather different. Even though they might appear the same size on the sky, they are very different in terms of size, because the M87 accretion disk is there placed relative to the orbit of Pluto. So you can see the accretion disk of M87 is huge compared to the orbit of Pluto, and that's how far Voyager has got so far. So if Voyager left from the center, it would only just have reached the accretion disk edge by now. By comparison, when we look at Sagittarius A star in our own galaxy, well, that is tiny by comparison. It's basically a little bit smaller than the orbit of Mercury, compared to larger than the orbit of Pluto. Huge scale difference, and it's only the distance to these objects that makes them appear similar sizes in the sky. But a reminder of just how much energy can come out of these things in terms of, remember, it doesn't come out of the black hole, it is the processes that occur around the black hole, where the gravitational forces are so large, the tidal effects are so large, as matter falls into the black hole, it can radiate energy. And here we can see that in this galaxy, Hercules A. There's Hercules A right in the middle. There's a little spiral galaxy next to it, so there's Hercules A. That spiral galaxy, we think, might be about the same size as the Milky Way, and it's roughly at the same distance. So this gives you an idea of scale. Remember, that's the size of the Milky Way. So Hercules A is a much bigger galaxy in the first place. But when we look at what the black hole at the center of Hercules A is doing, which we can see in radio waves, the jets it produces from a tiny black hole right in the center of that galaxy, those jets are coming across intergalactic space and are slamming into the intergalactic medium and producing shock waves over distances. Remember the size of the Milky Way? Well, these distances must be millions of light years. So the black hole itself is tiny, only the size of a solar system, yet it produces jets which have impact over millions of light years. That gives an idea of just the huge amount of energy that is pouring out of some of these black hole systems. A few years back, I gave you a talk in which I described what I called ancient light, because some galaxies have, quote, active galactic nuclei, in other words, black holes that are feeding at the centers of them. The most energetic active galactic nuclei are called quasars. And during the pandemic lockdown, I tried to take an image of one of these quasars without using a telescope. I just used my Nikon camera on a little star tracker, and I took a picture of that very unimpressive blob there, which if you blow up that blob, it's even less impressive. It's basically a pixel in the image that I took. But this blob comes from an object which is 25 billion light years away. And the light has been traveling for most of the history of the universe in order to reach my camera. It's so far away. Remember, the more distant an object, the faster it's receding from us by the Hubble law. This object is so remote, it's receding from us at about twice the speed of light. It was receding from us at twice the speed of light when the light left, and it's still receding from us at about twice the speed of light. But despite that enormous distance, it is still possible to capture the light from this object using a camera without using a telescope, simply because of the amount of energy that's being released by quasars because of this powerhouse of an engine at the center, a supermassive black hole. There must be a relationship between black holes at the centers of galaxies and the galaxies themselves. If we plot out here the size of the black holes that we found versus not the total mass of the galaxy, but the mass of the galaxy that appears to be in the bulge of the galaxy itself, we see the Milky Way, not a particularly large galaxy with a relatively small black hole of 4 million solar masses or so. And at the other end of the spectrum, there's M87, a huge galaxy with a huge supermassive black hole. And there appears to be a relationship between how big is the black hole and how big is the galaxy. But then we have a chicken and egg problem. How did this relationship come to be? Did black holes form and then galaxies form around them? Did galaxies form and then somehow black holes end up collecting together at the center? Are they the result of stars going supernova? But these galaxies seem to form very early on. The black holes seem to form very early on. The James Webb Space Telescope is looking back in time to try and understand the very first stars, the very first supernova, the very first black holes in the very first galaxies, because we don't really understand what this symbiotic relationship is between the black holes at the centers of galaxies and the galaxies themselves. Still an open question. But let me finish with the C of the ABC, which is galaxies grow by colliding and merging. Their origin is based on accretion. Black holes is a relationship we don't fully understand. Collisions is something that we think we can get a handle on. Galaxies grow by colliding and merging with other galaxies. When you look at an image like this, it all looks very sedate and serene. We know that galaxies are rotating. It might take hundreds of millions of years for a galaxy like that to rotate. Our sun takes over 200 million years to go round the center of our own Milky Way galaxy. But over its lifetime, it will almost certainly interact with other galaxies. Sometimes we get obvious clues. When we look out into the universe, some galaxies are isolated, but we have lots of examples, especially in the last 10, 20 years or so. We now have lots of examples of galaxies that are quite definitely interacting with their neighbors. Tidal effects are pulling galaxies, and we can clearly see the effect of galaxies merging together. But the full influence, snapshots don't give us the full story. We can only really comprehend the interaction of galaxies over billions of years, not by taking a series of snapshots, but by running a simulation and saying, how do galaxies interact with each other? And again, is the result anything like what we would expect? So here's a simulation in which a very massive galaxy is drifting in from the top, and another galaxy is drifting in from the bottom, and there's 100 other galaxies in there. But watch what happens not only to individual galaxies getting distorted, watch what happens when this galaxy gets closer. They're pulling on each other by their mutual gravity. They pass each other, and then gravity pulls them back again, and then after a little bit of a dance, they merge together and make an even bigger galaxy. That is how galaxies grow. Galaxies don't start off large. Galaxies start off small, and over billions of years, they eat their siblings, they eat their neighbors. And quite often what happens is large galaxies eat a lot of the smaller galaxies. We are fairly sure that the Milky Way has done that in the past. The Gaia spacecraft has been working out the dynamics of stars in our own Milky Way galaxy and has now built up a body of evidence that says we know that we have merged with other galaxies in the past. We know that we have merged with best part of 10 other galaxies, generally smaller galaxies, to build up the Milky Way as we see today. Some of the stars in the Milky Way do not belong in the Milky Way. They belong to other galaxies that we have subsequently eaten. Some of the globular clusters in the Milky Way, again, have come from other galaxies, and we have imported them, as it were. When we look at galaxy clusters, we often find galaxy clusters have got a lot of reddish elliptical galaxies in them, rather than the bluish spiral galaxies of the Milky Way, for instance, or the Andromeda galaxy. That's simply because they are more crowded. Galaxy clusters are crowded, so collisions are more likely, and when spiral galaxies collide, they tend to lose their spiral arms and end up producing elliptical galaxies. That's why the crowded regions of clusters tend to be crowded regions of elliptical galaxies, not crowded regions of spiral galaxies. We can see that if we look at a simple simulation from a few years ago, Triangulum galaxy, Andromeda galaxy in the Milky Way, we are fairly sure that the Andromeda galaxy is on its way towards us. There is some doubt as to whether it's going to be a head-on collision or not, but the Milky Way and the Andromeda galaxy are going to pass through each other. Stars are not going to collide. The stars will miss each other, but the galaxies themselves will collide, and a lot of the gas and the dust will mix together and produce a riot of new star formation as the two eventually merge together. We can see what that might look like in a series of snapshots. So at the moment, there's our own Milky Way galaxy, of course, seen from the inside, and there's the Andromeda galaxy, which makes a wonderful target for astrophotographers if you've got a telephoto lens. But if you're prepared to wait a little while, you won't need a telephoto lens. Because if you wait for another billion years or two, you're going to start to need a wide-angle lens, as it's going to fill the sky, and eventually the Andromeda galaxy is going to get so close, as it starts to pass through, it'll be impossible to tell which star came from the Milky Way and which star came from the Andromeda galaxy. As they literally pass through each other in about 4 billion years or thereabouts, there is going to be this, you can see all the pink here, this new star formation. The tidal effects of one body of gas interacting with another, not the individual stars, but all of the gas in the two galaxies, they will perturb each other and make the gas clouds collapse and make new stars. So galaxy collisions is not the end of the line for a galaxy. Au contraire, it's the start. It's a rebirth. It's new life coming to the galaxies. So yes, one will pass through each other, and it'll take quite a few 100 million years for them to settle down. So after 4.0 billion years, Andromeda will have passed through, and it might be possible to say those look like the stars from Andromeda, but almost certainly it would have dragged some Milky Way stars with it, and eventually they'll settle down into a large, probably elliptical galaxy, still with two nuclei. The supermassive black hole from our galaxy and the supermassive black hole from Andromeda are going to be orbiting each other for a long, long, long time before eventually they merge some billions of years into the future into one even larger supermassive black hole. What are we going to call this new galaxy? We could call it Milkdromeda. We could call it Aldrinki. We could call it Androe. We've got 5 billion years to decide, so I think we'll probably have a vote on it at some point and decide what this new galaxy is going to be called. But it is quite possible that because so much material of the two individual galaxies, not only colliding and interfering and perturbing each other, there's going to be an awful lot of material falling into that black hole and an awful lot of material falling into this black hole. At the moment, the black holes in the Milky Way and Andromeda are effectively quiescent. Very little is happening. Not much material is falling into those black holes. We're not getting huge outpourings of energy from either. But when the two collide, that's different. They will suddenly start feeding on the enormous amount of raw material that they then have. So the question is our new galaxy, whatever name we decide to give it, is it going to turn into a quasar? Is it going to turn into a galaxy in which so much material is falling into the black holes, so much energy is being released, maybe this new galaxy will actually be visible from way over on the other side of the observable universe, just like the galaxy I was showing before is actually visible to a camera here on Earth, even though it's 25 billion light years away. Maybe our own Milky Way/Andromeda galaxy is going to light up and actually produce a quasar-like result, which will be visible across the entire observable universe. So I've been telling you about the ABC, the accretion, the black holes, and collisions. So next time you're lucky enough to look through a small telescope, okay, it might only be a little bit of a fuzzy blur where you can just about make out the spiral arms. Either when you're looking at a galaxy through a telescope, or when you're looking at the amazing images that you see online or in magazines or on the sky at night or whatever. Next time you see any of these galaxies, hopefully you'll be able to remind yourself about the ABC of galaxy evolution. Thank you all very much.
Thank you very much.